Welcome back, section 4.2. So, null spaces, column spaces, and linear transformations. Now, if you recall, these words should look familiar because we studied them in, or we learned them, these concepts in chapter 1 and chapter 2. But there we learned them in the context of sets of the type Rn, sets of vectors. That's what we call them, like R2, R3, R4, and so on. But here now we are going to talk about these concepts in the context of vector spaces. So just to review the definitions, we call that the null space of an M by N matrix. So these null spaces and column spaces, they are connected to matrices. Okay, so if we have an M by N matrix, the null space of the M by N matrix A, some matrix A, is the set of all solutions to the homogeneous equation Ax is equal to 0. Well, in set notation, we can write it like this, that null of A is equal to the set of all x such that x is in Rn. This is important to note, that x has to be in the Rn space and Ax is equal to 0, and it should satisfy this condition that when it is multiplied on the left by the matrix A, we get a 0 vector. The column space of the matrix N by N matrix A is the set of all linear combinations of columns of A. Now, if we represent A in column notation, as we saw in chapter 2, I believe, then column A can be called as the span of A1, A2 up to AN. What does it mean by the span? Remember what type of vectors are in the span? They will be the linear combination of these vectors, which are the columns of A. There is a theorem here, theorem 2. It says the following two statements are equivalent. What do we mean by equivalent? That one can be replaced by the other, or one can be used in place of the other. So what are the two statements? One says the null space of an M by N matrix A is a subspace of Rn, which is what is in the definition, which is true. But that also means that the set of all solutions to the homogeneous equation Ax is equal to 0 is a subspace of Rn. So same thing. Now theorem 3 says the column space of an M by N matrix A is a subspace of Rm. Okay. Note now the column space of an M by N matrix A is all of the Rm. It will be all of Rm if and only if the equation Ax is equal to B has a solution for each B in Rm. Okay, here is a contrast between the column space and the null space. So the first point to note is that null A is a subspace of Rn, as mentioned in the above theorem, and column A is the subspace of Rm. Second, null A is implicitly defined and the column space is explicitly defined. What does that mean? It means the column space is basically in front of you. So you look at those columns and you know that some of them or all of them are going to make up the basically basis of the column space. And so they're in front of you, you just have to pick the correct ones or the right ones. But in the null space, you have to actually solve the equation. Solve the equation Ax is equal to 0, and then find those x's which are the solution. So in other words, actually the same thing. Now what do we do to find the vectors which are in the column uh, space of A, um, and find the vectors which will be in the null space of A. So to find vectors in null A, row reduce A augmented with the zero vector. Remember the matrix A and augmented by the zero vector. We can find the answers or the solutions for the null space. Now, a typical vector V, to find vectors in column space of A, find pivot columns of A. That will make up the basis of the column space. Number 4, a typical vector V, is it V or U, whatever, in null A satisfies the equation AV is equal to 0. So when you multiply V with the matrix A, you should get a 0 vector. Then it means that V is in A, otherwise not. V is in null A, and otherwise it will not be in null A. But in a typical vector, V in column space of A satisfy the equation that AX is equal to B. So as we said, column space it consists of vectors which can be written as linear combination of columns of A. Number 5, to find, okay, we are done with number 5, sorry. Vector, typical vector in null A satisfies the equation AV is equal to 0, whereas the typical vector V in column space of A satisfies the equation AX is equal to B. Number 5, to find if a given vector U is in null A, we compute A times V or U, or AU. But to find a given vector U is in column A, row reduce A augmented with U. Number 6, null A is equal to 0, consists of only the 0 vector if and only if the equation AX is equal to 0 has only the trivial solution. Now, column space of A will be equal to the Rm, the whole sub vector space Rm, if and only if the equation Ax is equal to B has a solution for each P in Rm. Number 7, null A is equal to 0 if and only if the linear transformation from X to Ax is 1 to 1. So up till number 6, we were talking about the matrix. We were looking at our differences considering the matrix A, but number 7 is talking about linear transformation. So you have learned, or you already know, that this can be the transformation, the type of transformation that we have seen are from like Rm to Rn. So it is saying that, and we also notice that this type of transformation actually can be converted into P of X equals AX, where A is the matrix of the transformation, standard matrix of the transformation. So this is the same A that we were talking about, M by N matrix A. So the number 7 is saying the null space will consist of only the 0 vector if and only if the linear transformation X, which goes to AX, is 1 to 1. So in other words, if we if we have to find if whether a given transformation is 1 to 1, we can calculate the, or we can evaluate the um, solutions, or look at the solutions of the homogeneous equation Ax is equal to 0. If we only get the trivial solution, the 0, 0, 0 solution as our answer, then it means that the transformation T is 1 to 1. Column on the right side, column space of A will be equal to Rm, the whole vector space Rm, if and only if the linear transformation basically is onto. But we say onto what? So from it maps Rm onto Rn. Now this can happen onto one thing. This can happen only when m is greater than or equal to n. If we have m is less than n, then we cannot have an onto. We might have an 1 to 1, but we cannot have an onto relation. The new thing here is kernel. This word kernel. Range is you are familiar with. So we talk about kernel and range of a linear transformation. A linear transformation T from a vector space V into a vector space W is a rule or a function that assigns to each vector V in the vector space V a unique vector T of X in W, such that T of U plus V is equal to T of U plus T of V. Because why? Because remember, T is linear. So, and T of C U is equal to C of TU. The kernel or null space. Kernel is the same as the null space. So the word kernel is used with transformations. Now, null space can be for any vector space or any subspace. The kernel or the null space of a linear transformation written as KER of T in parentheses is the set of all U in the vector V such that T of U is equal to 0. So all the vectors in V that are mapped onto the 0 vector of the W are in the kernel of that transformation. The range of a linear transformation T, written as range of T, is the set of all vectors in W. So here, all set vectors in W of the form T of X. So what does that mean? It means, now remember, X is your X is, sometimes we call X as pre-image. So here X is the pre-image and T of X is the image. So if you recall the set kind of an example, so here we have an X. If my function is named T, transformation T, and I have an X here, then this X is going to be mapped onto a T of X, and this is pre-image and that is image. Okay. If T is defined using a matrix by like T of X is equal to AX, then kernel of T will be equal to null of A. Okay. and range of T will be the column space of A. So okay, I will stop here. We will do the examples in the next video.